Welcome back, everyone, to our ongoing deep dive series exploring the online encyclopedia of integer sequences. Especially useful, we think, for number theory students.
It's a fantastic resource.
It really is. Today, we're focusing on quite an interesting one, A000007.
Ah, yes. A000007. It's a great example of, well, how seemingly simple counting problems can bridge different mathematical areas.
So what's the main idea behind it? What's it counting?
Okay, so primarily it counts the number of ways you can slice up a regular polygon 1 with n plus 2 sides into n triangles.
Right, using diagonals.
Exactly, n1 diagonals. And they can't intersect inside the polygon. But, and this is key, it counts inequivalent ways.
Inequivalent, what does that mean here?
It means we consider dissections the same if you can get from one to the other just by rotating the polygon or reflecting it. Symmetry is crucial.
Okay, so we're removing duplicates caused by symmetry.
Precisely. And interestingly, it also counts something called unlabeled maximal outer planar graphs on n plus 2 vertices.
Wow, okay, graphs too. That already sounds like a surprising connection. Maybe let's start with the polygon dissection part first.
Which I did.
If we take, say, a square, that's n2, so an n plus 2-sided polygon, a foregon, how does the inequivalence work there?
Right. For a square, n2, you need n1, so one diagonal to make n does 2 triangles. You can draw it one way or the other way.
Two ways.
But if you rotate the square 90 degrees, one diagonal orientation turns into the other.
Oh, I see. So under rotation, those two ways are actually considered the same way for this sequence.
Exactly. They are equivalent under symmetry. So for n2, the sequence value a2 would reflect this counting only the fundamentally distinct pattern.
Got it. So it's about the pattern, not the specific orientation. Now, how does this relate to the Catalan numbers? Because counting triangulations without symmetry, that's Catalan, right?
Yes, precisely. The total number of ways to triangulate a convex, n plus 2 Catalan, ignoring symmetry, is the nth Catalan number, C Catalan.
Yeah.
A very famous sequence. A000207, which we call AN, gives the count after you account for these rotational and reflectional symmetries.
So how do we get from CN to AN? Is there a formula?
There is. The OEIS entry provides it. It's a bit complex, involving Cn itself, and sometimes other Catalan numbers like Cn2 plus 1 or Cn3 plus 1, depending on n.
So like AN lns 2n plus some other terms?
Yes, something like that. Specifically AN2n plus Cn2 plus 1 4 plus Ck2 plus Cn3 plus 1 3. But those terms only apply under certain conditions.
Conditions, like whether n is even or divisible by 3.
Exactly. The structure of the formula changes based on the divisibility of n by 2 and 3.
Why would that be? What's the intuition there?
Well, it comes back to the types of symmetry that n plus 2 gon has. An even-sided polygon has different rotational and reflectional symmetries compared to an odd-sided one.
Okay.
And if the number of sides is, say, divisible by 3, you get additional rotational symmetries like 120-degree rotations. The formula is essentially using principles related to Burnside's lemma or polyenumeration.
Counting under group actions.
Precisely, even if not named explicitly. It accounts for how many triangulations are fixed or unchanged by certain symmetry operations to get the correct count of distinct orbits or patterns.
That's clever. It subtracts the overcounting that CON does by treating symmetrical copies as distinct. Okay, let's switch to the other definition you mentioned, maximal outer planar graphs, MOPs.
Yes, MOPs. It's quite a shift, seemingly.
What is a MOP exactly?
Okay, imagine drawing n plus 2 points, say, on a circle. Then connect them with lines, edges inside the circle. A graph is outer planar if all its vertices lie on the outer boundary or face, and it's maximal outer planar if you added as many non-crossing edges as possible inside the boundary, such that all the interior faces are triangles.
So all vertices on the outside, and the inside is fully triangulated.
You got it. And the amazing connection is that the number of these MOPs on n plus 2 vertices, when you consider them unlabeled.
Meaning you don't care which specific vertex is which, just the overall structure.
Exactly. That number is precisely AN, the same as the number of inequivalent polygon triangulations.
Wow. So the polygon's vertices map to the MOP vertices on the outer face.
Yes. And the diagonals of the triangulation map directly to the internal edges of the MOP. The triangular regions correspond perfectly.
That's a beautiful link between, well, geometry and graph theory. The unlabeled graphs maps perfectly to the inequivalent under symmetry polygons.
It does. It shows how these different perspectives are capturing the same underlying combinatorial structure. Counting up to isomorphism in graphs is analogous to counting up to symmetry in geometry here.
Okay, this sequence is getting more interesting. The OEIS entry also mentions Hexaflexagons. What on earth are those?
Hexaflexagons, they're fun. They are paper polygons, usually hexagons, made from strips of paper that you can fold and flex to reveal hidden faces.
Like a paper toy.
Sort of, yes. Quite intricate ones. The order n+2 relates to the number of triangular faces making up the flexagon. And remarkably, AN also counts the number of distinct hexaflexagons of order n+2.
No way. How does that connect?
It suggests the combinatorics of how these flexagons can be constructed and how their faces relate under flexing must have the same symmetry constraints captured by A000007. It's a physical manifestation of the abstract math.
That's incredible. Polygon divisions, graphs, and now foldable paper things. Does it stop there? I think I saw mentions of associahedra.
Right. The connections go deeper into abstract algebra and geometry. A000007 also counts certain types, specifically normally non-isomorphic realizations of an object called the associahedron.
And the associahedron relates to ways of grouping things, like parentheses.
Exactly. Its vertices correspond to ways of parenthesizing a product, which is another classic Catalan number problem, deeply linked to binary trees, and yes, back to Polygon triangulations again. It's all interconnected.
It really is a web. And there was one more, hyperbolic tiling.
Yes, it even connects to non-Euclidean geometry. It counts polyform shapes made of connected cells with end cells in a specific hyperbolic tiling called 3 infinity, where you don't distinguish mirror images.
Okay, my head is spinning slightly now. Polygons, graphs, flexagons, associahedra, hyperbolic tilings, all counted by A00000207.
It's quite a portfolio for one sequence.
But the common thread seems to be this idea of counting distinct structures once you factor out equivalences due to certain symmetries. Like you mentioned, Burnside's lemma and related ideas are lurking underneath.
That's the heart of it. How do we count things when we decide certain transformations don't create a genuinely new thing, as 00007 provides the answer in all these diverse contexts?
So, bringing it all together, A000207 counts polygon triangulations ignoring rotation and reflection, which is surprisingly the same as counting unlabeled MOPs, and also connects to hexaflexagons, associahedra, and even hyperbolic geometry.
It's a beautiful demonstration of mathematical unity. You start with cutting up a shape, and you end up touching on graph theory, topology, abstract algebra.
It really highlights the power of the OEIS to reveal these hidden connections. It makes you wonder, doesn't it? Considering how this one sequence bridges all these fields, what other profound links are just waiting to be discovered in that database?
What fundamental principles of symmetry are really at play here, unifying these seemingly disparate counting problems? It's definitely food for thought.
Absolutely. So if this has piqued your interest, we definitely encourage you to explore A0000000107 on the OES yourself. Look at its formula, the comments, the related sequences like the Catalan numbers A000008. You might find even more connections.
It's a rewarding exploration.
Well, thank you for joining us on this fascinating deep dive today.